Okay, now that we know a little bit about phase diagrams, let's delve into phase thermodynamics, the thermodynamics of phase transitions. All right, first let's talk a little more about the chemical potential mu. I want to show you that, in fact, similar to what we have for G, how G varies with temperature and pressure, we can write an equation for mu where instead of just entropy and volume, when we have for G, free energy, we instead have partial molar entropy and partial molar volume. All right, so let's start out. Mu is a function of temperature and pressure. Note that we have the number of moles not in here because this is a partial molar quantity. We've taken care of that. So like we've done for free energy and Helmholtz free energy and all those other things, we say that d mu will be how mu changes with temperature at constant pressure times dp plus how mu changes with pressure at constant temperature times dp. Remember that mu, I just write mu, was how G changes with number of moles at constant temperature and pressure. So let's go ahead and put that in here. So now we have d mu is how G changes the number of moles at constant temperature and pressure, how that quantity changes with temperature at constant pressure, plus, we'll substitute that in there, how G changes with N at constant temperature and pressure, and how that quantity changes with pressure at constant temperature. There should be a plus sign there. All right, now look at this. This is G. We're taking the derivative first with N and then with T, but G is a state function, so it doesn't matter whether we take it first with N and then T or with T and N. And the same way over here. So we can rewrite this equation as how G changes with temperature at constant pressure, number of moles, and then how that changes with N at constant temperature and plus, we're continuing this here, the derivative with respect to N of how G changes with pressure at constant temperature, then how that changes with N at constant temperature and pressure. And this would be a dp here, a dt, and this would be a dp. So we just switch the order of integration. Now, how G changes with temperature, constant pressure, remember from a previous lecture, that's minus the entropy. And how G changes with pressure at constant temperature, this is equal to volume. So we can rewrite this as how minus S changes with number of moles N at constant temperature and pressure times dt plus how volume changes with number of moles at constant temperature and pressure times dp. This we define, remember, as minus the partial molar entropy. So when you take a quantity and take the derivative with respect to number of moles, you get a partial molar quantity, and we'll denote the partial molar quantity with a bar above the quantity. And this you might also recognize as the partial molar volume. So we can rewrite this as minus S dt with partial molar plus V dp with partial molar. If we contrast and compare what we did for delta G, remember delta G is minus S dt plus V dp. So it's very similar, except that instead of entropy and volume, you have partial molar entropy and partial molar volume. Okay, so that's what is covered here. Interesting. So how chemical potential varies with temperature is minus the partial molar entropy. Same way with how chemical potential changes with pressure. Okay. Now, remember we said this was the master equation of chemical thermodynamics. Let's apply this to phase equilibrium. And in fact, we did that. So we said that if you just have two components, in this case, it's a single pure substance, but the two components are the components in two different phases. This means that the chemical potential of that pure substance in phase 1 is equal to the chemical potential in phase 2 when you have phase equilibrium at constant temperature and pressure. Also note that at phase equilibrium, well, what am I drawing here? Let me go over here. So we have delta G is delta H minus T delta S. So at equilibrium, delta G is equal to 0, and this equilibrium we're looking at is phase equilibrium. This implies that delta S is just equal to delta H over T. Okay, to make that a little more concrete, let's take a phase transition. Let's just take water, and we're going to say start that at, I don't know, liquid, and we're going to have H2O in the gas phase, and we're going to be in the phase diagram along one of those lines, so this will be in phase equilibrium. So for at phase equilibrium, when you have two phases coexisting, for water at 1 atmosphere, that would be 0 Celsius, phase equilibrium. For example, this could be 1 atmosphere and 0 degrees C, where ice melts or freezes, and in those conditions there you have an equilibrium. The chemical potential of water in the liquid phase is equal to the chemical potential of water in the gas phase. All right, so that's thermodynamically what we mean by phase equilibrium. The chemical potential of the substance in the two phases is equal at phase equilibrium. And then remember, I'll just draw the phase diagram here. We have pressure and temperature. So we have something like this. So what we're on along one of these lines, these phase equilibrium lines, under one of those lines, on one of those lines, we have to have the chemical potential of the two phases equal. So, for example, if this is solid, this is liquid, and this is gas, here along the liquid gas, so say any point along here, we have to have phase equilibrium. I guess what I said before, sorry, liquid to gas, duh. So rather than re-record this lecture, just let me say that there should be 100 degrees C. Duh. Liquid gas. All right, so right up here, 1 atmosphere, and at 100 degrees C, at that point, we're right there along that phase boundary. And along the phase boundary, in fact, any place along the phase boundary, this one or that one or that one, we have the chemical potential of liquid, or of one phase, equal the chemical potential of the other phase. Okay, so that's what we mean by this slide. Now let's talk about the Clapeyron equation. This is not the guitarist, Eric Clapeyron. In fact, it's spelled differently. So this is actually a guy who lived back in the 1800s, a dead white European male. He developed this equation here. At phase equilibrium, dP dt is the change in the partial molar entropy in going from one phase to another, divided by the change in volume, partial molar volume, in going from one phase to another. All right, so what does dP dt mean? Okay, so here we go. We refer again to the phase diagram, pressure, temperature. So dP dt is the slope of a pressure temperature diagram. So at any particular point here, you can use a Clapeyron equation to figure out what the slope is. Okay, and let's show that. Okay, So what we're going to do, let's say start from some generic substance A1 in one phase, and that's going to be in equilibrium with the substance in the second phase. So 1 and 2 here represent the two phases. We know when there's phase equilibrium, the chemical potential in phase 1 of this substance is equal to the chemical potential in phase 2 of that substance. We only have one substance, so I don't need to label these as A. We also know from the equivalent of the master equation for chemical thermodynamics that in phase 1, d mu in phase 1 is the partial molar entropy of phase 1 times dt plus the partial molar volume in phase 1 times dp. And you can write a similar equation for phase 2. This is the at equilibrium, we're going to equate these two, minus the partial molar entropy in phase 2 times dt plus the partial molar volume in phase 2 times dp. And now we're going to equate these two so that if you take an infinitesimal amount going this way, the change in chemical potential, d mu1, is the same as the infinitesimal amount if you go the other way. In other words, they're at phase equilibrium. So in other words, d mu1 is equal to d mu2. All right, so we can equate these two. Let's do that on the next page here. So that we have minus S1 in one phase dt plus the partial molar volume times dp in phase 1. That's equal to minus S in phase 2 plus the partial molar volume in phase 2 times, oh, I forgot the dt there, dp. All right, let's collect terms. Let's put the dt terms over here. So put that dt term over there and put that one over there and collect terms so that we have dt. And let's make this S2 minus S1. All right, so there's the partial molar entropy in phase 2 minus that in phase 1. That's equal to, and here's the dp terms. We put them over here. There's a partial molar volume in phase 2 minus the partial molar volume in phase 1. Or another way to write that, take that below here. Let's define this as delta S. So this is a change in the partial molar entropy when you go from phase 2 to phase 1. Or sorry, phase 1 to phase 2, final minus initial. And this will define or give a symbol delta V with a bar across it. And that's the final V2 minus V1, phase 2 minus phase 1. So we divide this here and we get how pressure changes with temperature along a phase line in the phase diagram is just the change in partial molar entropy when you go from one phase to the other divided by the change in partial molar volume as you go from one phase to another. And that is the Clapeyron equation. Again, that comes from, okay, we have phase equilibrium, means chemical potential of the two is the same. We say what chemical potential is in terms of partial molar quantities, and presto, we have the Clapeyron equation. Okay, so there it is. But wait, there's more. Here's the delta S, but we know at the phase transition, remember we said before, no, wrong way, at the phase transition, delta S is delta H over T. All right, so let's go ahead and redo this, putting in a delta H instead of the delta S. Okay. So at the phase transition, let's see, we have dp dt, we said was, by the Clapeyron equation, delta S partial molar, delta V partial molar. But we said that delta S is at the phase equilibrium, delta H divided by T, and this is delta V. So let's just integrate both of these. The integral of dP, we'll put the dt over there, that's equal to the integral of delta H over delta V, 1 over T dt. We're going to integrate this from initial to final, or actually from phase 1 to phase 2. Let's go temperature 1 to temperature 2. So what we have is delta P. We assume delta H and delta V independent of temperature. And of course we really should be putting partial molar quantities here. Forgot those. So delta P, we can pull those out of the integral. Delta H over delta V, natural log of T2 over T1. So that's where that comes from. So if you want to know how the pressure changes, all right, so this delta P is how the pressure changes. Let's go back to the phase diagram. So here's volume, this is temperature and pressure. So here's some line in there. So if we want to know a delta P, so here is delta P going from, say, T1 to T2, we can use this equation, use the enthalpy for the phase transition, divide by the volume, partial molar volume change to calculate, and then multiply that by the logarithm of the final minus initial to calculate, if we change the temperature, how much the pressure changes. All right, so that's kind of cool. All right, now let's do an example to sort of hammer this home. You may want to pause the recording here to read this, but basically what we have is sulfur. S8, that's the form of sulfur, solid sulfur on these conditions, exists in two phases. We have a rhombic phase below 95, and we got a monoclinic above 95.5, and this is at one bar at pressure. We have the density of the rhombic phase and the density of the monoclinic phase. We have the entropy. So let me call this the partial molar entropy change. Going from rhombic to monoclinic is that. Calculate the pressure necessary to make rhombic sulfur stable at 100 degrees. All right. Well, let's draw a little piece of the phase diagram here. We have pressure and temperature, and at 95.5 degrees C and at 1 bar. So why do I do that here? Why don't I make this a little clearer? Yeah. Oh, I guess everything goes away. That's interesting. Huh. All right, so everything goes away, so I guess I can just restart the lecture here. That's kind of cool. All right, so just let's draw the piece of the phase diagram that this problem is referring to. This is the pressure axis, and this is the temperature axis. We're saying at 1 bar and at 95.5, that's the phase transition. Why is that? Because below it you get one phase and above it you get another phase. So that's a point along the phase boundary. And just let's draw this. Okay, there's a boundary. So over here below 95 at 1 bar, you have the rhombic. And here above 95, you have the monoclinic. So at 1 bar, if you now go up to, say, 100 degrees C, at 1 bar, you'll be in the monoclinic. What you want to do is to increase the pressure, so now you're at the rhombic. So the rhombic will be the stable phase. So we want to have a pressure change to bring this point at 1 bar and 100 degrees from the monoclinic up into the rhombic phase. So what should that pressure difference be? Well, we know from the Clapeyron equation that dp dt is some quantity, or let's use finite differences. So delta P will be those quantities, which we know what they are, times delta T. So we now have the delta T, we can calculate delta P. What's inside there? Well, you remember that was how the partial molar volume changes in going from one phase to another, divided by the partial molar volume change. Partial molar entropy change divided by the partial molar volume change. So that's the proportionality constant between pressure and temperature. Essentially, it's the slope of this line, just as we said, slope of that line. So let's get busy and calculate it. This we were already given in the problem as 1 joule 1 joule per mole Kelvin. Right, so that's what delta S was given the problem. How are we going to figure out how the volume changes when we go through that phase transition? And just to be clear, the phase transition we're looking at is S8. That's the form of sulfur, 8 sulfur atoms in a molecule. That's in the rhombic phase. Goes to S8 in the monoclinic phase. So that refers to the partial molar volume or partial molar entropy change. This refers to the partial molar volume change. All right, so what we can do, if we can figure out what the partial molar volume is of both phases, we take the final phase, that, subtract off that, and that will give us the partial molar volume. So what are we given in the problem? We're giving densities. Oh, that's interesting. So that's the volume occupied by a gram, but the partial molar volume be the volume occupied by a mole. Oh, okay, so I think we got it. So again, V2, say this will be correspond to the monoclinic. So the 2 will correspond to the monoclinic. That is equal to 1 over the density, which is 1.96 gram per centimeter. So this gives you how many centimeter cubed a gram occupies. And let's convert that to SI units. So let's multiply this by 10 to the minus 6 meter cubed per centimeter cubed. And it'll be clear later on why we want SI units. And now we got to convert the grams of sulfur to moles of sulfur. And that's S8 is 256 gram per mole. So this comes out to be 1.31 times 10 to the minus 4th meter cubed per mole. That's the partial molar volume of the monoclinic phase. Let's do that for the rhombic phase. That'll be 1 over the density of the rhombic phase. There's a density of the rhombic phase is there. We use the density of the monoclinic phase already. This would be 1 over 2.07 gram per centimeter cubed. We'll multiply this by 10 to the minus 6 centimeter cubed. There you go again. Sound like Ronald Reagan. There you go again. In color, okay. Ronald Reagan was president in 1980 and 1988. He was also an actor. So we have meter cubed per centimeter cubed. All right, convert to SI units. Get rid of that gram, convert it to mole, 256 gram per mole. So the partial molar volume of sulfur in the rhombic phase is 1.24 times 10 to the minus 4th meter cubed per mole. So the change in partial molar volume will be the final, which is monoclinic. We're looking at the transition from rhombic to monoclinic, so here's the final minus the initial, That's the rhombic phase. So it's 1.31 times 10 to the minus fourth minus 1.24 times 10 to the minus fourth. So that comes out to be 6.94 times 10 to the minus sixth meter cubed per mole. So that's a change in partial molar volume. So, as we said, delta P, we're converting from infinitesimal to finite changes, which is essentially assuming that that phase boundary line is linear over delta T. That is equal to delta S bar over delta V bar. Delta S bar, given the problem, 1.00 joule per mole Kelvin. Delta V, delta V is, we just calculate what that is, 6.94 times 10 to the minus 6 meter cubed per mole. Did I put a 6 there? Yes, 10 to the minus 6, that's correct. And that comes out to be 1.12 times 10 to the fifth joule per meter cubed Kelvin. Okay, so there's a proportionality constant between delta P and delta T. So the change in pressure we have to have in order to make rhombic the stable phase at 100 degrees will be 1.12 times 10 to the fifth joule per meter cubed Kelvin. Delta T, we want to go to 100, and we're starting at 95.5, and in our earlier discussion, delta C is the same as delta K. So the change in pressure comes out to be, so what do I get here? It should be around 6, about 6. Now I'm going to say this is, now let me not do that yet. So this is equal to, where did I get it? Here it is. 5.0 times 10 to the fifth joule per meter cubed. All right. The SI unit of pressure is the Pascal. Pascal. Let's just figure out in fundamental units what the unit of pressure is. All right, so pressure is defined as force per unit area, and force is mass times acceleration over area. All right, and this will be the mass times, say, delta x over delta t squared divided by area. Okay, so let's just put that in. Mass times length divided by area would be length squared, and this would be the units, SI units of time squared. Okay, and so let's actually continue on here. Let's put in the SI units. Well, let's simplify that a little bit first. That will be mass, one of the lengths cancels out, over length, times time unit squared. Let's put in SI units. SI unit of mass is kilogram. SI unit of length is meter. SI unit of time is seconds, seconds squared. And this is called, this unit, this SI unit is called a Pascal. Pascal. All right. Now let's go back up here. Let's see, our units we got for delta P will be joule per meter cubed. Is that a Pascal? Yeah, I think it is. But just to show you, a joule per meter cubed, a joule is a kilogram meter per second squared and we have the meter cubed here. That's just equal to a kilogram per meter second squared. Oh, look, so a joule per meter cubed is the SI unit of pressure, which is Pascal. All right, one further thing is that 1 bar is defined as, that's not the SI unit of pressure. The SI unit of pressure is Pascal. 1 bar is defined as 10 to the 5th Pascal. All right. Why are we doing this? Well, we started at 1 bar, and we want to know what the pressure will be. And I didn't really say that. Let me just stick that in here, in bar, when you go to the 100 degrees. All right, so back up here. So we have delta P, we calculated, was 5.03 times 10 to the 5th. We said joule per meter cubed, and that's equal to 5.03 times 10 to the 5th Pascal. And that's generally true. I mean, if you use SI units throughout, then whatever quantity you're calculating will have the SI unit. All right, and this is equal to, we have to multiply, because we want it in bar, that's what we're asked to calculate in the problem. Sort of, okay, so it's 10 to the 5th, so sorry, 1 bar over 10 to the 5th Pascal. Okay, I just love the eraser function. Okay, so this is 5.03 bar. All right, so delta P was P final, that's what we want, minus P initial. So the final pressure is the initial pressure plus delta P. The problem, the final, or the initial pressure was 1 bar, and the delta is 5 bar. So the final pressure you have to be is 6 bar. So what does this calculation do? Well, it says that, if you go back to the original phase diagram here, now you have to go up to 6 bar in order for the rhombic phase to be stable at 100 degrees C. Okay, kind of neat. We calculated those. That's what physical chemists really get excited about, calculating things like that. All right, so that's that example problem. Now, if the phase transition involves a gas phase, here you get the Clausius-Clapeyron equation, which was given just sort of thrown out there in introductory chemistry. For instance, calculate the vapor pressure at one temperature, given the vapor pressure at another temperature, and the enthalpy change of the phase transition. Well, we're now going to derive this equation, which was just sort of thrown out there in introductory chemistry, the Clausius-Clapeyron equation. All right, so let's start with the Clapeyron equation, and we'll make it the Clausius-Clapeyron equation. So dP dt, this is the Clapeyron equation, is how the entropy, partial molar entropy, changes during the phase transition divided by the partial molar volume, how that changes. And let's, again, take some generic thing in the liquid, and now we're going to make it into the gas. So it's important to write something like this, so that we know what these deltas refer to. Now this delta refers to the gas minus the liquid. All right, so let's look at the delta partial molar volume. This will be what we end up with, gas, partial molar volume of the gas in that phase, minus the partial molar volume in the liquid phase. I claim that this is about equal to the partial molar volume in the gas phase. Why? Liquid per mole has a smaller volume. So the partial molar volume, the volume occupied by 1 mole of the liquid, is much less than the gas, so we can approximate the molar volume change as just the partial molar volume of the gas itself. And now let's use an ideal gas equation. So that's another approximation. Here's our first approximation. Ideal gas means that V over N is equal to RT over P. So the partial molar volume per mole, that's what that is RT over P. So this is equal to RT over P when we make the ideal gas approximation. All right, and now we also know that the delta S, the entropy change, going from another at equilibrium, is just delta H over T. We'll put that there, meaning partial per mole at the phase equilibrium. All right, so let's substitute that in there, and let's substitute that in there. And what do we get? Well, we got dp dt. Substituting in for delta S, we got delta H over T. And substituting in for delta V, we have RT over P. Now that's not really arranged, but just let's rearrange this. This will just be delta H over R, and this will be 1 over T squared, and this will be pressure. Okay, so that's all that thing written that way. So let's integrate both sides. So this would be, we'll take the P over here, so we can integrate over P. So from some initial pressure to some final pressure of 1 over P dP, that's equal to, we're going to integrate this side, delta H over R, 1 over T squared integrated over T. All right, so this is the natural log of P2 over P1. That's equal to, let's assume delta H is independent of temperature. So we pull that out of the integral, delta H over R. And if we integrate this with respect to temperature, we're going from T1 to T2. That's minus, multiply minus 1 over T, 1 over T2 minus 1 over T1. Okay, because I think, yeah, the integral. So T squared, that's right. Or in other words, let's just rewrite this, is minus delta H over R, 1 over final temperature minus 1 over the initial temperature, T1. That is the Clausius-Clapeyron equation. There it is. So now what we did, we used the Clapeyron equation, which we got from a fundamental understanding of phase equilibrium, and we got the introductory chemistry, just doing some substitutions here, making a few approximations. Approximations is that the partial molar volume of liquid is much smaller than V and also an ideal gas, which assumptions we didn't really mention in introductory chemistry. We get the Clausius-Clapeyron equation. Pretty cool. Well, that's it for this part of the lecture, and then we have one more part of lecture 10.